Now, humans broadly categorize our own modes of thought along holistic or analytical lines, and the current conception of time is particularly analytical in nature. And so that infinitely divisible model allows for sophisticated analysis in related fields, but it is also likely that an approach like that destroys some of the information that could be present in a more holistic model. Now, by contrast, a model in which coherence is extended not just across space but also time allows for a more mixed approach. So if we view some processes as holons occupying bounded regions of space and time, that opens the door to more holistic approaches to certain problems, and it prevents the loss of data that further subdividing them would entail. So by recognizing the type of data which is lost, if that kind of process is subdivided anyway, then we gain a sense of the kind of additional problem-solving capabilities that can be viewed by a holonic or a holistic theory of time. So one capability like that may be an explanatory mechanism for phenomena like pre-stimulus response, reference 26. So if we view time not as infinitely divisible backdrop where nothing can affect a previous state, then no matter how close these states are in fact, then experiments like Spottiswoode and Mays violate our most basic assumptions about the universe. If we instead view time as an uneven or bubbly medium, within which some process can't be subdivided without losing information, then this class of phenomenon is perfectly in line with our assumptions. Some information would exist in superposition across a span of time and be accessible around a triggering event, not just at or after the event itself. So if this assumption holds water, and there's numerous experiments that indicate that something of this nature must be in play, reference 27, then the question arises of whether that dynamic can be usefully employed, and this is where the relevance to divination comes in around this theory. So much of the motivation in any study is related to practical applications, and practical applications can demonstrate a controversial theory far more convincingly than any amount of experiment in the lab, which is why I'm very interested in taking a kind of practical approach to this set of questions. Now, time is often considered external to the experiments in quantum mechanics, reference 28, and experiments are generally constructed on the assumption that an observation causing a wave function collapse can happen at any arbitrary point in time. And although this is borne out by observation, it does not address the fact that observations can't be made with arbitrary precision, nor the possibility that some processes could resist observation or change their behavior due to observation. So the localized nature of time in relativity is sufficiently well established at large scales that a theory of quantum mechanics compatible with it would likely have to account for the effect. Phenomena like the quantum Zeno effect are observed at very small scales, but it may be possible to apply the same principle to very large scales as well. Consider, for example, the interpretation of the quantum Zeno effect put forth earlier, which suggests that in order to move, a particle has to entangle with a state adjacent in both time and space, and that preventing entanglement by repeatedly observing the particle in one place prevents it from gaining the necessary transition energy to be observed anywhere but its initial state. And now consider the creatively named phenomena of spaghettification. So spaghettification refers to the fact that when an object is accelerated to near light speed, such as while approaching an event horizon, it appears to stretch along the direction of its velocity. If we apply a similar interpretation to this phenomenon, the logic of entanglement is required for motion would predict the very fast-moving object is entangled with so many adjacent states along its direction of motion that its stretched set of states appears as a single holon with a longer extent along one direction. Now, we tend to think of the Copenhagen interpretation as punctuating a period of wave-like behavior with an instant in which collapse reveals an object in a real and perfectly localized state. But in fact, this localization should only occur to the degree that we know the timing and result of the measurement. So we tend to think of the wave-particle duality as a strict binary, with a wave pattern collapsing into a local particle upon observation. But it's probably more accurate to say that a wave pattern's distribution narrows to fit within the measurement error of the observation causing the collapse. So we imagine a wave collapse as a normal distribution becoming a probability 1 distribution, where the measurement actually placed it. But it would probably be more accurate to replace the normal distribution of our wave function with a narrower normal distribution, bounded by the accuracy of our measurement apparatus. And the collapse of the probability wave creates additional certainty, but the new narrower probability distribution is not qualitatively different from the previous one. Now, near light speed objects could be seen similarly as having such wide probability across one dimension that measuring its position along this direction does not collapse its position beyond a certain point. In other words, it resists collapse. So in some sense, the question of whether thinking in terms of fields or particles makes better predictions could be seen as an expression of the same dynamic. Rather than see the wave-particle duality as a binary, we could instead say that the nature of the interaction determines whether we see a wider or narrower distribution of states. A very precise measurement narrows the possible states to a very small set, while a more general measurement allows a wider range of possibilities in the system with which a given observer interacts. Now, this quality of resisting collapse is important if we're to move from a theoretical to a practical investigation. Now, time to decoherence can be calculated giving the right combination of conditions and assumptions, reference 29. And if we consider it in the macroscopic sense, it would correspond to the ability to maintain multiple potential states simultaneously. Now, by way of contrast, the ability to enter flow state consistently seems to require not simply existing in a superposition of multiple states across a period of time, but also being able to recognize the preferred chain of events. Now, the latter seems to primarily require domain knowledge, and it's been hypothesized that diligent practice followed by relaxation is a necessary precursor for entering flow state, reference 30. And anecdotally, flow seems to require visualizing the next step in the process as it unfolds, which is only possible with an accurate domain knowledge. And the more accurate the domain knowledge, the more accurate the visualization. So if a flow state is analogous to a superposition of multiple states, and domain knowledge allows us to observe a more optimal path through the possibilities, we would assume something else determines whether enough states are included in the first place. So given that successfully entering flow state requires a large percentage of mental resources to be dedicated to a single task, a similarly large amount of mental energy seems to be dedicated to including potential states in the brain's mental model of the process. So if the human brain's functionality lies in partially modeling the universe, it stands to reason that dedicating more mental resources would allow a more complex model, which runs and evaluates more scenarios in parallel, to be made. And paradoxically, so might the inclusion of fewer time steps. So consider this is a classic example of a Go player who seemingly wastes a move by placing a stone where it's not helpful to his strategy until very late in the game. Modeling possible progressions of a lengthy game probably requires beginning at a fixed state of the board and diverging the various models from there. So each fixed state envisioned like that requires a new model to be made starting at the hypothetical state. The more skilled a player is, the farther from a desired outcome he can place his setups, while still accurately modeling the steps in between. And essentially more skill allows a player to treat a larger block of time as a single holon, with multiple possible states internal to the holon being modeled. Now, another codeterminant to flow is creativity, which we might be able to conflate anyway, with the introduction of a novelty. And human experience is generally that doing anything novel is more difficult than doing something familiar of similar complexity. And Sheldrake's model of the universe as forming habits rather than running on static laws, reference 23, would offer an explanation for that behavior. But during flow, introducing novelty becomes easy, or at least the difficulty of it is indistinguishable from the difficulty of entering flow. So if we take both Sheldrake's morphic resonance theory and the subjective feeling of easy novelty in flow states at face value, then something peculiar must account for their seeming contradiction. And an obvious subject for study would be the nature of time in both models. So by positing that events tend to repeat once they happen, Sheldrake's theory implies a particular direction to time. And quantum mechanics, on the other hand, it doesn't have a particular direction to time. In fact, experiments like the quantum eraser show that this bidirectionality isn't just a weird function of the math. It actually shows up in experiments that humans can observe. So the holonic model of time may be compatible with both theories by presenting time as discrete units, which are individually internally bidirectional, but can be arranged directionally when multiple ones cluster together. And psychological flow in this theory presents a means of having fewer, larger holons relative to the default mode. So the default mode models the environment as a larger number of smaller and thus less complex holons. And by reducing the number of holons in the model, flow allows for fewer, richer, and less predictable interactions between the holons that make up the model.